Hello. Now, this is the final installment on the part concerning ray optics or geometrical optics. Thereafter, we'll be dealing with the wave optics part. So, the last bit has the derivation of the lens maker's formula. So, the lens maker's formula uses the concept of the refraction through a single spherical surface that we discussed in the previous video. And here, therefore, we'll be considering two surfaces joined together that form a complete lens. Again, I've taken the example of the convex lens. You can use the case of concave lens as well. So here the principal axis passes through the optical center of the given lens, and you have a point object to be lying somewhere on the principal axis to the left. Let that position be O, and then you have a light ray to be incident on the first surface. Now what happens over here is that you have the first medium to be having an absolute refractive index mu1. The second medium is within the lens to be having an absolute refractive index mu2. Again, coming back to the first medium where the absolute refractive index was mu1. Now, as opposed to the previous derivation that we did for refraction through a single spherical surface, here we have a double spherical surface, and those two surfaces, let me name them as surface 1 and surface 2. Now what's happening is that first surface bends the light ray through a certain angle. Now it would have continued in that direction had there been no second surface, and it would have touched the principal axis somewhere over here where you are obtaining the image probably at the point I dash. But that's not to be, because the second surface will bend this light ray further into some other point. It is just like the case that we had obtained for two thin lenses in contact, uh, where the first lens would have bent the light ray to a certain point, and the second lens bends that light ray further. Now we have these two surfaces, and let the surface 1 have a radius of curvature as r1, and the second surface have the radius of curvature as r2. So those are the two things that we are considering over here. Now, as far as the refraction through a single spherical surface is concerned, we put it for the first surface. So for the first surface, we have the refraction through the single spherical surface that we did in the previous video. What we have is, it goes exactly in the same manner, where we have mu2. Now the image distance in this case would have been v dash had there been no second surface. So that remains the image distance for the first surface, and this remains the object distance, which is u, for the first surface. So we have mu2 over v dash, which is the image distance, mu2 being the second medium which would have, had that continued, that would have produced the image at I dash. So mu2 over v dash minus mu1 over u, that would have led to mu2 minus mu1 over r1, where r1 is the radius of curvature of the first surface. So this is the all of the equation that we are observing right now is the refraction for the first surface. Now for the second surface, we have the case just interchanging, because mu1 comes in place of mu2 and mu2 comes in place of mu1 because the mediums are interchanging. So what we have is a mu1 over, now the image for the second surface is obviously at a distance, let's say v, which is the distance of the point I from the optical center. So this is at v, that's okay. But what about the object distance? Now again, this is the case of virtual object distance, and the medium is obviously mu2, because mu2 is the first medium now, and mu1 is the absolute refractive index of the second medium. So you have a mu2 over the virtual object distance, because had that light ray from the first surface not been bent to the point I1, then the second surface wouldn't have bent the light ray to the point I. Now, if this light ray would have bent in some to some other point on the principal axis, then the second surface would have bent the light ray at some other point. So again, we are having the case of virtual object distance in this case. Again, as we have the refractive indices to be interchanging, so we have mu1 minus mu2 over here divided by the radius of curvature of the second surface, because we are concerned with the second surface over here. Now if we add up both these equations, what we get is mu2 over v prime cancels out, and what we are left with on the left hand side is that mu1 over v minus mu1 over u to be equal to, well, I can keep the mu2 minus mu1 form in common. So taking that as common, this term goes to the negative side. So that means I have 1 over r1, because that was there, mu2 minus mu1. But if I'm interchanging the denominator numerator over here, instead of mu1 minus mu2, I'm taking mu2 minus mu1, then this denominator term obviously becomes negative, or that term entirely becomes negative. Now, as we can see, we have mu1 to be the common factor on the left hand side, on the numerator of the left hand side. So we have 1 over v minus 1 over u to be equal to the mu1 goes common and gets divided over here, mu2 over mu1 minus mu1 over mu1 is 1, and then we have 1 over r1 minus 1 over r2. Now, as you know, the refractive indices, when taken in that fashion, we have discussed already this one while during the starting video, that mu2 over mu1, that is the absolute refractive index of the second with respect to the absolute refractive index of the first, is nothing but the refractive index of the second with respect to that of the first. So this is mu2 with respect to 1. Now, generally, the first medium, if we are considering the case as air or free space or vacuum in this case, then the lens is just suspended in the first medium, and the refractive index here thus obtained here is actually the refractive index of the material of the lens. So we have mu2 with respect to 1 minus 1, 1 over r1 minus 1 over r2. And then on the left hand side, because this is a lens which is having a certain image distance for a certain object distance, and the left hand side represents the left hand side of the lens equation, thin lens equation, so the right hand side must represent the other term which is to the right hand side of the lens equation, that is 1 over f. So 1 over f is equal to this factor that we are seeing on the right hand side, which is the refractive index of the medium of the lens with respect to the outer medium minus 1, and the bracketed term contains the difference between the reciprocal of the radii of curvature. Now, as we know that the reciprocal of the focal length gives the power of a lens, so the power of a lens is equal to mu minus 1, the refractive index of the material of the lens, minus 1, 1 over r1 minus 1 over r2. So this is what we get as the power of the lens. So that's more or less the case of the lens maker's formula. What the lens maker does is that he prepares your lens according to the power that your eyes require. What he does is that he will shape the uh, both the surfaces of the lens, that is the surface 1 and the surface 2, according to the requirement, such that you get a desired power, because the material of the material would be of a certain refractive index which is of a known value over here. So this is fixed for a given material of transparent medium that is being used as the lens. And the other two things that the lens maker must be concerned about is the shaping of the lens, so that the radii of curvature of both those sides of the lens are adjusted such that you get a desired power as per your requirement, maybe for your spectacles or maybe for your maybe for a magnifying glass or anything like that. Now, although I said that this is not the last installment for the ray optics part, because we still have the case of refraction through prism and the case of dispersion, and then we will be ending the ray optics, and exactly not the end again, because we will be dealing with uh, the case of optical instruments, that is. So we have a lot of things aligned ahead of us, but this is an important consideration uh, for the exam point of view and for the board's point of view. So the lens maker's formula is a very important thing which you must relate with the previous case that we discussed in the previous video. Now, in case you are just asked to derive the lens maker's formula, you will be using this exact condition that we have used over here. But if you are asked to consider the case of refraction through a single surface and derive that as well, that will be for a different question. So keep that in mind. You are using the case of refraction through a single spherical surface, and then you are obtaining the lens maker's formula. So that's more or less the case that we had to discuss in this video. We'll be continuing with ray optics, of course, but that is for the next upcoming videos. Till then, thank you for watching.